Hi everybody, welcome back. Well, hopefully you got a little time to review our previous slides in the last homework about the first two properties of the function limits. Well, the first one we have learned is called the uniqueness. Okay, the second one we have learned so far is called the locally bounded. Theory. Okay, so today we're going to continue to the third one, which is about, well, the one we have already listed here is called the locally sign preserving property. Well, that sounds a little awkward, but we're going to see what it's like. Well, it is kind of related to the second property. It's locally bounded. So let's see one example here. So for example, we have a function f here, fx. So for example, we say if we're approaching to this point x0, right? So we're gonna have the fx, the limit to be a certain value, which is obviously bigger than 0. And also naturally, or to say intuitively, you can see from the graph that, or in your imagination, we definitely always have a small range around the x0, right? Maybe from here to here. So within this range, the function value fx is also positive. So similarly, if we have a limit here, okay, so maybe this is another one called x1. So we can see that at x1, the limit of fx, we would say the limit of it when x is approaching to x1 is smaller than 0. So of course, around the fx, the function value fx is also smaller than 0, which means when x is between a certain small range about this point. Okay, so that's the basic idea of the third property of limits called the locally sign preserving property. Well, so let's write down the precise definition using the language of mathematics. So here we have a new theory. Okay, so if we have a limit, this is what we've been looking at many times, so which equals to a, I have some, okay, so so if we have this limit existing, so for example, we say a is bigger than 0. A is bigger, text mode. Okay, let's see. So if a is bigger than 0, so like what we have shown just now, we're sure that then we have, so when x is approaching to this, certain point x0, where we have the limit a, so when x is approaching to that point, we're going to say the function value fx is also bigger than 0. So similarly, if we say that, blah, 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 if fx limit, is approaching to this point, however, at this time, the limit is smaller than 0. So we can say that, of course, so when x is approaching to x0, we can say that fx, the function value, is also smaller than 0. All right, so that's basic the definition of the third property. Well, hopefully you don't find it difficult because, well, it's actually, in my own opinion, maybe a little simpler than the definitions of the previous two we have learned so far. So let's continue to look at how we're gonna prove this. I mean, so if a limit exists, positive or negative, well, we're so sure about the function value around it is also positive or negative accordingly. Of course, we can see it or we can imagine it intuitively, but in mathematics, it's also recommended for us to prove it very strictly, if possible, right? So let's look at how we can prove this. So we also want to write down the okay, let's change it to another color. So I would say the proof here. Okay. All right, so we have learned the definitions of the function limit and also the three properties about the limit. So if we want to prove, this limit property as well as, the other properties, we have to write down the definition of the limit first. So we say that, let's write down the, function limit again. So I will use a simpler version here. So we say that, for a function which has a limit around a certain point, right? So we have, so for any epsilon, which is, of course, bigger than 0, which can be as small as possible, but have to be positive. So when x is approaching to x0, so we can say that the fx and a's distance is extremely indefinitely small, which means it is always smaller than this positive number epsilon in your imagination, which is as small as possible. All right, so let's start from this one. So let's do some, high school calculation here. So this one can be further changed to, a minus epsilon smaller than fx and then smaller than a plus epsilon, right? Yeah, that's, the converted form we have. And we understand that, epsilon is positive and it can be as small as possible. It's arbitrary small positive number. So why don't we choose? So why not? We just choose, the epsilon's value as half of a. It is good, right? Because a is positive. Yeah. And here we choose half a, which is also positive. So that satisfies the definition of epsilon. And then let's continue. So on the left side, we have a minus, yeah. Okay. Have this. Okay. Smaller than fx. And this left side can be further converted to a over 2. Smaller than fx. All right? Yeah. So by now, well, I think most of you have found out what's the point here. We understand that a over 2, the half of a, is also positive. So this time, if fx is bigger than a positive number, so this means fx is also, we can say, positive. So this has, help us to prove, the third property of limits. So, of course, this is the first, situation where the limit a is a positive number. You can also try yourself after this session of class for the second situation where a is smaller than 0. Well, it is very similar, so you can just try it a little bit by yourself to practice it, okay? All right, so I know that some of you cannot wait to jump to the actual question we're going to meet. So here we have one example. So let's see. So if we have a limit fx when the x is approaching to x0, which is noted here by f0, okay? So now also we have the condition that the limit of this complex formula, it's not that complex actually. Okay, so here we have this equals to f2 when the x is approaching to 0. Okay, so here we're gonna change this to 0. Okay, yeah. All right, so given those two statements, so what we can conclude concluded from. So at x equals to 0, okay, so we're gonna have the maximum value or the minimum value or the just extreme, no matter if it's maximum or minimum, or just some value, but we cannot determine if it is extreme or not. Okay, so of course we're gonna apply the property we have learned in today's class to this question. So if you want to try it first, it's highly recommended. So you can pause the video and come back later. So if you have no idea, so let's work on it together. Well, this is actually a very good example to practice, the third property of the limit. As we can see that, well, since we have, this limit here when the fx is over 1 minus cosine x, right? And also it is minus 2. According to our theory, it means when the x is around 0, so this fx over 1 minus cosine x is smaller than 0. Yeah, so we can write this down. So we can say, so fx over 1 minus cosine x when x is, when the x is approaching to 0, must be smaller than 0. Okay, so at this time we can say, because 1 minus cosine x is positive. Why? We can try it because for the trigonometry, right? The cosine x, function graph looks like this. So when x is approaching to 0, of course, it is going approaching to 1 here. So that's why, because x can never be 0 exactly, so 1 minus cosine x must be bigger than 0. Okay, so if the denominator is bigger than 0, we can say that fx can deduce this one. Okay, so fx must be, smaller than 0. So in your imagination, in your mind, you can imagine for the function fx, it may look something like, for example, this is the 0. Okay, this is the 0. So before, 0, maybe we're approaching from the left or from the right. So it seems like we can never reach 0 exactly, but we can approach to 0. So the function may look something like this because fx, other than 0 must be smaller than 0. Okay, or something like this, whatever. You cannot always imagine. Okay, where will we find the shape of this function graph later? So let's continue. We will discuss how to calculate the limits in our following sections. But today, I just want to let you know something about the limit calculation. So here, if we say the limit of, I would say fx, because we're caring about fx here, when x is approaching to 0, right? Okay, it's not that easy for us to find right now, but we can do the identical transformation. Remember the concept about math philosophy? Yeah, so if you don't have something, you can always constitute, something to make it happen. So this can be transferred to limit x is approaching to 0, fx over 1 minus cosine x time 1 minus cosine x. Okay, so for here, okay, so further down we can just, put the limit operation for each, terms here. So we can say that, for this one, we already understand what this looks like. So this one is approaching to 0 because cosine x, when x is approaching to 0, equals to 1. So 1 minus cosine x, when x is approaching to 0, is approaching to 0 actually. Okay, so for this one, what is this one? Well, don't be afraid, this one is the given condition, here, right? Yeah, so when fx over 1 minus cosine x when x is approaching 0 is given as minus 2. Okay, so we can say minus 2 times 0. So this one gives us 0. Alright, so it seems like when we get back to our graph, we can further refine it. Now see here, we can confirm it looks something like this, right? So the limit of fx when the x is approaching to 0 is 0. Yeah, to this point. But when fx is not, equals to 0, of course, the fx value must be negative. So on both sides, we can imagine something like this with the 0 excluded. Okay, so if we have something like this with the 0 included, right? So we can say that this must be the maximum because at the point x equals to 0, the function value reaches to its extreme, which is the maximum version. Okay, so at this time we can say yes, A is correct. Alright, so that's all for today's lecture. So I think you guys cannot wait to get into the next one because in the next lecture we're going to talk more about a specific limit calculation, which is more related to most of the text questions. But since we have talking about so much about the limit properties and the definitions, hopefully you guys can always review and grasp the ideas, master the theorems here, because these are the fundamental knowledges to guide us through the calculations and applications for the test and for your future careers. Okay, have a nice day and see you next time.